A very good morning to our lecturer, Dr. Noaini, and everyone watching. My name is Chin Kai, and we are from Home Group Ed. And today we are excited to present our filtering analysis map for this digital signal processing project. So, for our main objective was to process a heavily degraded audio file containing the spoken word 000 and reliably eliminate the harsh background telephone line static and hiss. To explain how our system accomplished this, I will kick off the presentation by introducing our first core milestone, that is sampling. So, as displayed on our back section here, sampling is defined as the process of converting the continuous time analog signal into discrete time signal. Mathematically, this is modeled by the formula where we capture specific amplitude value at a fixed interval determined by our sampling period Ts. Xn equal to Xnts. So, looking at our backlog code, we use the function bracket x with fx equal to audio rate bracket file names to import the audio file. This extract the discrete amplitude data point into vector x and read the native sampling frequency fx, which is 8000 Hz for our project. We then create a discrete time vector t using the relationship t equal bracket 0 with length x minus 1 divided fx to make out each individual sampling position based on Ts. Finally, to visualize this digitization, we plot the first 200 sampling using the stem bracket t1 with 200 and then x bracket 1 with 200 and then the fill function. So let's take a close look at the general graph on the right. The top subplot shows the originally noisy signal over full 1.8 second duration, where the thick blue profile reveals the continuous background noise envelope. The bottom subplot zooms in closely on our discrete signal within a tiny fraction of a second from 0 to 0.025 seconds. By using a stem plot instead of continuous connect wave line, we successfully expose the digitized matrix structure of the audio data. Our core observation here is that the continuous analog subwave has been cleaned functionally into discrete, isolate numerical data collected over time. This confirms that the signal has been properly digitizing and fully ready to process by our filter pipeline. I will now pass the presentation over to my teammate to discuss how we analyze this system using convolution.
Hi, I'm Chia Yu Yang, and I will present about the part convolution. Convolution is a mathematical operation that combines an input signal and the filter's impulse response to produce an output signal. In digital signal processing, it calculates the time domain effect of a linear time invariant system on an input waveform to achieve the filtering. So let's see the formula of the convolution. Yn equals to xn multiplied by hn. And here we have two input sequence. The first is the xn, which is the original noisy audio signal, and the second is the hn, which is the FIR impulse response. After we make the convolution of these two input sequence, we will get the Yn, which is the audio signal after the filtering. So let's move to the main part of the manifold and graph. So here, step 2 is try to execute the first input sequence, which is the Xn, and here is the graph. And step 5 is try to execute the graph of the second input sequence, Hn, and here is the graph. So at step 8, we are trying to make the convolution of these two input sequence. So as we can see here, by calling the mat function of the conv s hash, the MATLAB is mathematically slice the impulse response across our noisy signal to compute the filter output. So in conclusion, the convolution process successfully attenuated the high-frequency background noise. Compared to the initial massive waveform, our output shows a much clearer and more distinct amplitude envelope, confirming that our DSP filtering approach was effective. So that's all from me. Thank you.
Hello, Li Jiale here. So my keyword for this analysis is Z-transform. The Z-transform converts a digital signal or filter equation from the time domain into Z domain. Instead of working with the difference equation directly, it represents our filter as a transfer function, h of Z. This is useful because it lets us check two important things, whether the filter is stable and how it will behave across different frequency, both of which are hard to see from the raw time domain equation alone. So here's the formula. So h of Z equals y of Z over x of Z, expressed as a ratio. The numerator contains the b coefficients and the denominator contains the a coefficients. These a and b value come directly from the filter design. In our case, an 8-order Butterworth bandpass filter. In MATLAB, we get this transfer function alone using the Z-plane function, which plots the filter poles and zero on the complex Z-plane, shown here on the right. The circles represent zeros, and the cross, in this case, the marker cluster near the center, represent poles. So now before generating this plot, the observation here is it wasn't actually obvious from the raw coefficients alone whether our filter will be stable. Higher order IIR filter like ours can sometimes produce plots that drift outside the unit circle, which would make the filter unstable and cause the output to diverge. But after plotting, we can clearly see that all 16 poles are clustered inside unit circle with maximum magnitude about 0.96, safely under 1. So this confirms our filter is stable. This matters practically too. It will guarantee that when we apply field in our next step, the filter audio output won't blow up or distort, and we can move forward confidently to compare the frequency spectrum before and after filtering.
Hello everyone, this is Madan from Group A. I'm here to explain about discrete time Fourier transform, which we also call it as DTFT. DTFT changes a digital signal from the time domain to frequency domain. It also helps us to identify different frequency components and unwanted noises. And the formula here of DTFT shows both forward and inverse transformations. And when we go to MATLAB code, it shows the FFT spectrum before filtering and after filtering, and generates the frequency axis and plot the frequency spectrum also. And when we come to the analysis, N is the length, which also helps us to find the total number of samples in the signal. And X converts the signal from the time domain to frequency domain. And F creates the frequency axis in hazards. ABS calculates the magnitude of each frequency component, and plot displays the frequency spectrum. And here, when we come to the graphs and it shows the frequency spectrum before filtering and after filtering. So from the graph, we can find the difference of the frequency spectrum. So, and when we come to the observation, before filtering, the spectrum contains unwanted noise frequencies. After filtering, the noise frequencies are reduced. DTFT makes it easier to analyze the signal in frequency domain. Thank you.
Hi everyone, in this part, I will be presenting the windowing method for FIR filter design. The windowing method is a technique where we start with an ideal filter and infinite impulse response and truncate it in the time domain using a finite length window function. This gives us an approximate finite impulse response. And the next is formula. First, we calculate the cutoff frequency, omega c. So this is equal to omega p plus omega s over 2. Second, we define the ideal impulse response, st of m. This takes the form of a sinc function. Sin divided by pi n when n is not equal to 0, and it converts to omega c over pi when n equal to 0. Third, we multiply this ideal response by the window function wn and apply a time shift to make it closer. So the final result is the finite length sequence Hm defined for n equals 0 to n. This gives us the closer FIR filter coefficient. And here is my MATLAB implementation. I set the filter m to 20 with omega p equal to 0.2 pi, omega s equal to 0.3 pi. And I use a Hamming window of n plus 1. Then I use the FIR1 function passing in the order the normalized cutoff frequency and the window to generate the filter coefficient B. After that, I plotted the impulse response and use FREQJ to compute and plot the magnitude response. So looking at the result on the right, the magnitude response is nearly flat in the passband close to 0 dB and drop off sharply after the cutoff frequency with the stopband significantly attenuated. So below that, the impulse response saw a finite set of coefficients that are symmetric about the center, which confirms that this is a linear fast FIR filter. To summarize, the FIR filter design using the windowing method successfully approximates the ideal raw pass filter. Because we use a Hamming window, there are small ripples present, but the side lobes are effectively suppressed. So overall, the filter.
Hi, I'm Zikai and I'll talk about bilinear transformation. This slide explains the bilinear transformation, which is used to convert an analog filter in the S domain into a digital filter in the Z domain. It preserves filter stability and avoids frequency aliasing. In the MATLAB code, FC1 and FC2 set the lower and upper cutoff frequencies at 300 and 3400 Hz. These values are normalized using the Nyquist frequency to obtain Wn. The Butter command then designed an 8th-order digital Butterworth bandpass filter. MATLAB internally applies the bilinear transformation and produces the numerator coefficients B and denominator coefficients A. The resulting filter allows pitch frequencies between 300 and 3400 Hz to pass while reducing frequencies outside this range.